All right, hi everyone. Good morning. It's my pleasure to introduce Jiaming. He hails from Stanford, being a student of Stefano Ehrman, and he has worked a lot on generative models and applications to imitation learning in the form of generative adversarial imitation learning, aka GAIL. And before Stanford, he was an undergrad student in Tsinghua. Were you one of the many bright Tsinghua undergrads who were sent overseas to learn the trade of the Western nations?
Not really. I think we are generally pretty open to research and.
Okay, the answer is yes. Anyway, so without further ado, I think Jiaming should take it away. Can't wait to see what you're up to.
All right, thanks. Thanks, Greg, for the introduction. I'm Jiaming, and as Greg introduced, I'm a third-year PhD at Stanford University. And today I'm very excited to share about some of my works concerning some applications of deep generative models. So I assume everyone here are slightly familiar with deep generative models and their impacts. Apparently, deep generative models are very successful in generating images, such as the very recent Big GAN and GLOW. And these models are very successful, that we can almost generate very realistic cheeseburger images. And also, there are a lot of applications in terms of audio, such as WaveNet, or also the text generation. However, I guess these progress mainly comes from the fact that you have a lot of compute. So that is doable in Google, that is doable in Microsoft, but I guess as a PhD student at Stanford, we don't have that privilege in the academia. So what we are trying to think about is some different applications in terms, apart from these very dominant applications of deep generative models. So today I'm going to talk about two potential applications that might be useful as applied by generative models. And the first is imitation learning. So we first introduce a distribution matching view of imitation learning, and then I will come into my topic of the talk, which is multi-agent generative adversarial imitation learning. And the second topic, if we have more time, is fair representation learning. Here we will try to introduce information theoretic notions on latent variable generative models and how we can learn controllable fair representations in a principled manner. So first, let's go to the imitation learning topic, which I will introduce, where I will introduce multi-agent generative adversarial imitation learning. This is joint work with Hongyu Dorsa and Stefano Ehrman. So first of all, reinforcement learning. So as we all know, we want to learn policies in reinforcement learning, and sometimes these are very high-dimensional and even raw observations. So for example, we have an environment, and our agents try to interact with the environment, which receives a reward and tries to optimize for maximum reward. So the fact that there is a reward is crucial to the success of reinforcement learning. For example, we can have the agents to play Pong and try to get a higher score. And the reinforcement learning agents basically takes in this image representation and produces an action. But as we just mentioned, reinforcement learning needs a cost signal. And in terms of Pong or chess, it's very easy to define a cost signal. However, in many other applications, such as self-driving or language generation, it is often very difficult to find the good cost signal. And if we don't have a good cost signal, then we might learn some policy that are unexpected behaviors. So one approach to mitigate this problem is through imitation. So it might be hard to give a cost function for self-driving, but we all know, most of us know how to drive. So we can use humans to provide expert behavior from some unknown human policy. And this is represented as a sequence of state action pairs. We are thinking of this as sampling from the expert demonstrations, for example, human. And our goal is to learn the cost reward, or the cost function, or the reward, or the policy. So what we did before in an experiment was we tried to imitate the behavior demonstrated here by taking in the input pixels and producing the right actions. Although here we are showing this partially observable case, we currently discuss only the fully observable case just for simplicity. So the problem setup. So here is our RL formula. the RL formula here tries to maximize the expected reward under a policy, while trying to maximize the policy's entropy. So here, the entropy is introduced in order to distinguish between potentially different policies that have the same reward, and also to address the issue that you can get the same policy just by scaling your reward by 2. And this is also useful in terms of proofs later on. So here we have a reward function, and we use reinforcement learning to obtain optimal policy. And this is done by interacting with the environment. And also, if we have the expert's trajectories, we can try to use inverse reinforcement learning to obtain a reward function. And through this loop, we can start from the expert trajectories, generate a reward function via inverse reinforcement learning, and then we can generate the optimal policy via reinforcement learning. So here, the assumption is that the expert is acting as the optimal policy under a certain reward, and we want to try to recover the reward. So one intuitive way to design this is to use this IRL formula. So the expert we try to give experts higher reward, and everything else would have a smaller reward. So essentially, we are trying to assign higher reward to expert actions and smaller reward to other actions. And this would be a way to measure the distance between policies. So one other way to introduce introduce regularization in the reward function. So one way is to introduce this psi of R, which is a convex reward regularizer. And this is useful in the sense that we might have some kind of prior knowledge over what kind of reward we might want to learn. And this allows us to pick the rewards that are preferable to us. So we are also this reward regularizer also have the property in that it is sort of trying to measure the distance between our learned optimal policy with the expert's trajectories via a similarity measurement based on psi. So there's a theorem that was introduced in the 2016 Generative Adversarial Imitation learning paper, was that this psi-regularized inverse reinforcement learning implicitly seeks a policy whose occupancy measure is close to the expert. So the occupancy measure is essentially the distribution of state-action pairs visited by the policy. And this similarity is measured by the convex conjugate of psi. So by introducing a psi, we are implicitly trying to give a similarity measure between the generated policy and the expert policy. So the theorem is stated here. So by combining the IRL psi operator with RL, we obtain a similarity measurement between the occupancy measure of pi and pi e, which is the expert. So here's the takeaway. So we have this theorem which states that inverse reinforcement learning is trying to find a policy which is similar to the expert as measured by psi star. And this is quite different from the typical IRL definition, because typically we are trying, the IRL definition finds the reward first, and then tries to find a policy based on the reward. And this alternative view is very closely related to the generative model viewpoint, which tries to match two distributions. So we are trying to match the expert's state-action pair distribution from our own generated state-action pair distribution. And by adding this regularization, we can generalize existing frameworks, because no regularization is also a type of regularization. So one form of this algorithm is called generative adversarial imitation learning, and it uses this specific form of regularizer. This might look very complicated, but essentially this is sort of defining a regularizer that is different from the regularizer that was used in the previous work. So some of the previous work used a regularizer such as the reward is linear with respect to some features. And there are also other different kinds of regularizers. So what generative adversarial imitation learning, or GAIL, does is it tries to use a possibly more flexible regularizer such that it could find a better reward function for the recovery of the policy. So here, what's interesting is that the previous psi that we introduced was actually closely related to generative adversarial networks. So the conjugate of this psi is actually just the objective for GANs. So we are essentially trying to sample from the expert policy, and then our policy generates their own state action experiences, and we can use a discriminator to just simply compare whether that's from the expert data or that's the sample generated from our policy. So by comparing this, we are able to learn a policy that is very similar, that produces the trajectories that are very similar to the experts. So this is also another demonstration of how this is done. So here, because we have a black box simulator in the case of reinforcement learning, we cannot do regular backpropagation as done with the generative adversarial networks. So we have to use like reinforcement learning to produce the samples that generates higher reward. So this is some results that we had like in last year's NIPS, and we are able to like generate. The input is like driving demonstrations, and we try to learn this policy from the raw pixel inputs. OK, this is not displaying, but well. So what we basically show was we were able to show the driving policy based on the visual inputs directly, and produces the self-driving actions just simply based on the state action pairs given by the expert. So the next thing that we might want to think about is the case of like multi-agent environments. So for example, here are like two types of environments where the blue and red, green are the moving parts are the agents, and the blacks are the like obstacles or the objective points. So one interesting thing to think about is like, can we automatically extract the goal of these agents? So by intuition, we can think of the blue agents are trying to match go to the certain objectives, and the red and green agents are acting like a predator-prey scenario where the red is trying to chase the green. It could be easier to understand this as a human, but it might be complicated to recover this reward function by just by the demonstrations alone. So here, in the multi-agent scenario, the setting is slightly changed from the single agent one. So here we could have multiple cost functions, and we use a multi-agent reinforcement learning setting in a Markov game scenario, which is a generalization of the Markov decision process. And we generate the policies of multiple agents. So we have from like agent 1 to agent k, we have multiple. We have the policy for each agent. And for example, we can have a like driving scenario where the two agents could drive on either the left or right. And if they both drive on the same lane, they will crash, so they will receive a worse reward. But if they drive on different lanes, they will receive like a positive reward. So this the inverse reinforcement learning process is also similar in that we give the expert trajectories for each agent, and then we try to use some type of multi-agent inverse reinforcement learning to obtain the reward functions, and then we can use the reward function to recover the agent policies. And we hope that by using this regularizer, we could also recover like each of the agent's policies. Yes?
So in the multi-agent scenario, what precisely should I think of as the meaning of the expert trajectory? Should I think of as there is an expert who's effectively acting as a centralized controller for each one of the agents? Should I think of there is a separate expert controlling each one of them? And if so, am I sort of already in some kind of a converged equilibrium state because they might be adapting to each other?
Yeah, that's a very good question. And exactly that's what we are going to explain in the next slide, next like two slides. So what our question here first is that can we design like a multi-agent inverse reinforcement learning algorithm that tries to match the occupancy like measures or the distributions of the expert and agent policies? So our problem is like, can we design for the multi-agent setting? Can we design a similar operator that was like very close to the IRL setting? that sort of recovers the occupancy measure. So here, this is a very good question about like what even is multi-agent reinforcement learning. So in the single-agent reinforcement learning, it's easier because we have the single reward, and the goal is simply to maximize the agent's own reward. However, in the multi-agent setting, if we are not in a cooperative case, then it's possible that the other agent's reward might actually depend on, one agent's optimal policy might depend on the one of other agents. For example, if we are in a rock, paper, scissors scenario, if my opponent always choose rock, then paper is my optimal policy. But then if my opponent changes his policy, then my own policy would also change. So we need a notion, like a different optimality notion compared to the traditional optimal policy case. And one of the case that we can think of is the Nash equilibrium, which is like a very commonly selected equilibrium state for multi-agent or game theory settings. So Nash equilibrium intuitively says that basically no agent can achieve a higher reward by changing its own policy while fixing other policy fixed. So here what we are saying is like for all the agents, if one of the agents change its own policy, it will receive like a lower reward, or a reward that is not greater than if it hadn't changed the policy. So I hope that this would answer your question.
But you are assuming that the demonstrations you get are after the experts have converged to such a Nash equilibrium.
Yes.
Which is potentially a bit dicey because convergence to Nash equilibrium can take a really long time.
Yes. So yes, there's a problem that maybe given the reward, the experts have a lot of a Nash equilibrium. I have a reward and there's a lot of Nash equilibrium, and also there's the problem with even convergence to a Nash equilibrium. So we currently are only talking about very simple scenarios to sort of make a connection. And I think there's also a lot of future work that could be done in this direction where we reduce the number of assumptions we make.
I mean, at a high level, do you have a sense of whether you are focused more on competitive versus cooperative scenarios, or do you not particularly care?
Currently, we're trying to not focus directly on cooperative or competitive scenarios, but we'll talk about that later. Mm-hmm. I think the way we could do this is to still utilize the reward regularizer, so that if we have some prior knowledge about what the reward is going to be like, then we are able to recover the reward. Otherwise, I think there are scenarios where you essentially could recover multiple rewards that explains the behavior. So one of the ways to formalize the Nash equilibrium setting is to use this constraint optimization problem. So here, what we are trying to we want to try to minimize this objective function subject to the constraints. So here, the objective function is similar to the Bellman equation for the policy, and we want to propose a value function for the policy. And we want to subject to the constraints that the reward by deviating from the current policy is never better than the value function that you already get by running this own policy. So this constraint optimization problem is more complicated than a single agent case because there are multiple agents, and there are issues of there are potentially multiple solutions. The solution, the argmax is not even convex, but we try to make more assumptions in order to deal with this. So here the objective is trying to find a value function via value iteration, and the constraint is that our set of policies have to satisfy Nash equilibrium. So here we have to assume that the expert policy is the unique Nash equilibrium under the proposed reward function, and that the expert is basically the unique global optimizer for the primal problem. This assumption is definitely not true in some of the cases and in some of the rewards, but to make things simpler to analyze, we currently make this slightly strong assumptions. So for the primal problem, we can write this Lagrangian form, which basically gives a multiplier to each of the constraints. And if we just maximize for the multipliers, we are able to this is exactly the same as the primal problem. However, if we evaluate the performance of a policy via this, we can just get the expert policy is always have an objective of 0, but for the other policies which are not in the Nash equilibrium, we can just make the multiplier to infinity. And if this is our reward and this is how we compare the policies, it is not very useful because anything that's not the expert is like infinity. So this is not very useful. So this is different from the IRL setting because the IRL setting didn't actually assume that you have to be on the equilibrium state. So it can compare the margin between two policies via the reward. And similarly, we also try to consider a case where we try to soften the function that compares the policy and the expert policy and the policy of individual agents. So we can choose the specific Lagrangian multipliers such that it creates a lower bound, and the lower bound is soft, but it can also compare the performance of different policies. So the G function was not very suited for computing the distance between policies, and we try to construct a smooth lower bound of G by choosing the specific Lagrange multipliers. So there are two steps that we could do this. So the first step is we can choose equivalent constraints so that we change the constraints, but we don't change the optimal solution of these constraints. The reason we want to do this is we want to increase the number of constraints so we are more flexible in the choosing of Lagrange multipliers. So the intuition is very similar to the TD1 learning, that learns the difference with the one-step return and just the multiple steps of returns. So if I have a k-step TD target, I can just simulate the environment for k-steps and use the value function as the t plus k-step. So equivalently, we can also introduce a Q function that is similar to the one-step Q function in the sense of multiple steps of Q functions. So we can basically change the constraints into this value function greater or equal to the multiple step K function, and we can prove that this optimizing the new problem still ensures that the solution is the Nash equilibrium. And the second step is to find the reasonable Lagrange multipliers that creates a smooth function for us to compare the distance between the policies. So considering the new Lagrangian, where we introduce Lagrange multipliers for each of the generated trajectories, and here we compare the Q function and the value function here. And here the tau means the length t trajectories for each agent I. So interestingly, we can show that the Lagrange multipliers can be chosen as some probability of generating the trajectories. So for any two policies, pi star and pi, let's say our Lagrange multiplier is the probability of generating the sequence with the agent I being pi and all other agents being pi star, then we can show that this happens. So you can essentially write this down as a difference of reward. So on the right-hand side, the left part is how the reward of agent I if it uses pi and all the other agents uses pi star. And the other part is where the agent I uses pi star and all the other agents also uses pi star. So intuitively, you can think of this as a scenario where you essentially treat all other agents as part of the environment, and you do it separately for each single agent. So under this scenario, we could reduce this into a simpler form, although this still requires us somehow to have the expert policy somehow. Then we can use this following a multi-agent IR operator, which also introduce a irregularizer on the reward function. Here, the reward function is a vector where we try to produce a reward function for each of the policies. And we can show that this strictly generalizes the previous inverse reinforcement learning operator when the number of agents is equal to 1. So similarly, here we want expert policies to have higher reward, and we want everything else to have a smaller reward. So what is the connection between this multi-agent IR operator and the occupancy measure scenario? So we can show that if we are allowed to assume that the reward function is additively separable, so that we are adding the reward function regularizer to each of the agents like separately, then we can show this, this property that combining multi-agent RL and multi-agent IRL operators can also lead to a case where we are comparing the occupancy measure between two policies. This apparently has a lot of limitations. For example, this cannot deal with like zero sum, the reward where the reward is zero sum. So because if the reward is zero sum, then the reward function regularizer cannot be like additively separable because the regularizer has to be like interconnected. So intuitively, this could be treated as like a very simple. Yeah.
So if I were in a zero sum setting, then shouldn't I just be able to actually do the agents completely separately? Because I mean, I'm trying to think: is there a way to actually use the fact that basically, oh, I see, but you're not really doing this interactively. So I'm trying to see if there's a way to use the fact that when we run no-regret algorithms separately for each agent, then they anyways converge to Nash equilibrium in the setting of zero-sum games.
I think the difficulty is that we assume that we don't interact with the experts in any way. So this is mostly the limitation. Like
so if you are in a dagger or aggravate style setting where you have interactive access with the expert, then this would not.
Well, if we have interaction with experts, we can just essentially let all the other agents be experts, and they are like part of the environment. So you could even basically reduce to like single agent settings. So that is not very interesting. So what we're trying to do is we try to use a more general setting where we cannot interact with the experts, and there is some limitations to it, at least in the current state. So I think one way to potentially like alleviate the zero sum case is like if we know some of the trajectories are like suboptimal, are like they're not in the Nash equilibrium. So maybe in these cases we could deal with the zero sum cases like more efficiently. So our practical algorithm basically uses multi-agent reinforcement learning to simulate the samples from our models, and also we are trying to use like multiple discriminators to compare the distributions generated by each agent. So we can also use different types of like incorporate our knowledge on the reward structure via the regularizers. For example, if you know that the agents are cooperating, then we are basically use a shared discriminator for all the actions. Or if we don't know anything about the reward regularizer, we can use like a separate discriminator. Or in the zero sum case, what we could do is we use one part using the expert policy, and the other part is our agent's policy, and we can use this trick to learn some reward. But the problem is, in the zero-sum case, here we cannot interact with the environment because we cannot simulate the expert beyond like more than one step. So this is ways to incorporate our knowledge on the reward structure just via the regularizers, and we show that you could write the regularizers psi in some way that satisfies these cases. So in the top row, we are trying to make these trajectories have higher rewards, and in the bottom row, we are making these to have lower rewards. And here are some experiments that we did. So here in the top row, the green line is the expert reward, and the gray line is the like random policy reward. We normalize this and try to compare like different methods. So two methods that are like slightly blue in the code. Code colors are like behavior cloning, which is essentially supervised learning given state and action pairs. And the other is like the single agent GAIL case, where we try to just use single agent GAIL. And in the red lines are cases where we either assume the agents are sharing the same reward, or we don't assume the agents are sharing the same reward. So interestingly, they are all performing much better than behavior cloning and GAIL, but their performance are relatively similar. In the second setting, we are considering like two cases where the agents are not cooperating, as sort of competing with each other. So this is very hard to evaluate in terms of reward because there's not a single reward. So what we do here is we try to use a baseline algorithm. Here we are using the agents learned from behavior cloning, and we use an adversary to compete with the agent, the baseline agent. So if we are comparing with the same baseline agent and gets higher reward, then our method is better. So here it turns out that in some cases the zero-sum agent performs better, and in some other cases the decentralized agent performed better. We also did this experiments on some like robotic control tasks where we have this. Let's see. So can I show that? Can I click on the slides somehow? Wait. Let's see.
You have to enable embedding.
I did embed it. I guess maybe I'll just show it this way. Yeah. So here is a demonstration where you have multiple agents trying to move this plank and also moving forward, and we are assuming that our demonstrations are suboptimal in the sense that in our real environment, simulated environments, the plank becomes like lighter and our agents have more strength. So in the case of behavior cloning baselines, let's see. In the behavior cloning baseline, if you try to like transfer to an environment where the planks are lighter, the agents are trying to use too much force to push this. So the behavior cloning was not performing very well. And sometimes like one of the agents clashes each other, or some of the agents are like just using itself to push the plank forward. And with multi-agent GAIL, the advantage is that you have the environment. So the environment itself would provide us some sort of like additional supervision, so that by comparing this, by matching the distance between state-action pairs, even though the action is not exactly correct, if you try to like match the state pairs more correctly, you can lead into better behaviors, even though the expert demonstration itself is like suboptimal in your new environment.
What's the intuition?
So the intuition is that the expert is demonstrating in an environment that's different from the environment that we are trying to learn on. And the behavior cloning is definitely false because the actions are suboptimal. And in the multi-agent scenario, we are trying to match the state action distribution. So even if we don't, because action dimension is typically smaller than state distribution, so it's also possible that we have a solution that matches the state distribution, but not necessarily match the action distribution perfectly. So by matching the state distribution, you can still generate behavior that that makes sense, even as we transfer the environment dynamics.
So should you just try to match the state distribution only always?
What?
Should you just try to only match the state distribution always then to have robustness? Like,
yes. So yes. So I think yeah. Actually, so I think most of the environments that we test on doesn't really require your reward to depend on the actions. Mostly we design our reward on the states. So I think like it's possible that if we use a discriminator that only discriminates on the states, it could also work. But we haven't discussed that in more detail, and that's it's slightly different from the case where we have it's slightly harder to discuss in the terms of like measuring occupancy measure, because then the distribution might get more complicated, and the policy and occupancy measure is probably no longer one-on-one. Yeah.
But I could have done exactly the same experiment for the first part of your talk, right?
Yeah.
Just a single agent case, I can also point out that behavior cloning is maybe not as robust compared to the occupancy measure regularizer that you had.
Yes.
Did you actually run a version of this which is not about multi-agent but just single agent?
I personally haven't done it on a single agent case. Yeah. Yeah. So moving on. So moving on, the conclusion is that like essentially, we can treat reinforcement learning as a dual of an occupancy measure matching problem. And this is very connected with generative modeling and generative adversarial networks. And in the multi-agent cases, this is complicated by the fact that we might have multiple or alternative optimality notions. For example, in this case, we are trying to use Nash equilibrium, but there are also other types of equilibrium notions that is possible. And under certain cases, we can link multi-agent imitation learning to occupancy measure matching. And this is slightly restricted in the fact that we might have to assume the existence of a unique Nash equilibrium, or the case where we need the reward regularizers to be additively separable. So the limitations obviously exist, for example, in the zero-sum case. And in order to move forward, I think maybe the best course of action is to introduce more types of data or scenarios that is slightly weaker than the fact that we have and can interact with the experts, but slightly stronger than the case that we cannot interact with experts and we only have the expert trajectories. So that's the first part of the talk, which talks about the imitation learning scenario. And the second part is trying to learn what we call is fair and controllable representations. So the setting of the talk is we have X, which is the features of an individual, and U as the sensitive attribute, such as gender. And C is our classification classifier, which takes in X and U and tries to predict some values. And Y is the target variable, which is the ground truth value. And Z is the representation that we might transform X and U into, which are used for downstream tasks. So here, our goal is to make accurate predictions while protecting the sensitive attribute. So one instance of this could be that we want to give loan to people according to their credit score, but somehow be fair to their race information. And there are multiple notions of fairness. So three of the most dominant notions of fairness are demographic parity, which essentially assumes that your prediction and sensitive attributes are independent. So they have zero mutual information. And the second case is called equalized odds, which means that these two variables are independent, conditional on the ground truth label. And the third case, equalized opportunity, tries to make the prediction and the sensitive attribute independent, conditional on the ground truth label being 1. So the problem with these multiple fairness notions is that not all of these notions can be satisfied at once. And there exists some impossibility theorems that tries to show that you cannot satisfy multiple notions. And since there's the notion of fairness might be deeply related to the social norms and the culture, so it might be the case that if some solution satisfy the fairness criteria of maybe one definition, it might be very bad in terms of fairness in the second definition. And I think it is very important to find a trade-off between multiple fairness notions that are relatively fair in all of these notions. So in terms of representation learning, we can try to learn a representation Z first, from the X and U, and then we can try to use Z to predict the labels. So this is somewhat called data preprocessing in the fairness literature, where we are trying to preprocess the data into Z. And by preprocessing, we can make fair decisions with Z, no matter what we do after this. So two desiderata that we want to make is to learn fair and expressive representations. So the first condition is that we can try to maximize the mutual information between X and Z conditioned on the sensitive attributes. And the second criteria is fairness, is that we want to minimize the mutual information between U, the sensitive attribute, and Z, the representations. So here we are assuming the fairness criteria is demographic parity, but we could also generalize it to equalized odds and equalized opportunity. So for sake of simplicity, we'll first talk about the case of demographic parity. So this could naturally lead to an optimization problem, which tries to maximize expressiveness under some fairness constraints. So assume that we have a prediction model called Q phi that tries to predict the representation Z from x and u, which is like a function mapping or distribution. And the data distribution, we can assume it as, we don't denote it as like q of x and u. And the constraint optimization problem under the demographic parity notion of fairness is simply just we try to maximize mutual information between x and z and try to, under the fairness constraints. So this epsilon quantity is actually can be determined by the user, which is like a hyperparameter of this problem. So the problem of the previous, the constraint optimization problem is that these quantities are not like really tractable. By tractable, I mean you can have like you can do stochastic gradient descent like in an unbiased measure if you only like subsample from the data set. So here, you actually need to compute these quantities, you need some sort of posterior, to compute the posterior maybe via Bayes rule, and that requires integration and makes it intractable. And because we only have this prediction model that has the tractable log density. So the solution that we propose is that we use upper bounds and lower bounds for mutual information that allows us to connect this with the previous methods and also with like variational autoencoders. And by optimizing for this solution, we can obtain solutions that are methods that are tractable. So here, we first introduce a parameterized distribution called P of theta, which predicts x from the z and u. And we can actually show that the mutual information between x, z, conditional on u has this equality. So the second term here is the constant entropy, and the third term is the like GAIL divergence, which is always greater than 0. And the first term is usually called like reconstruction error in the variational autoencoder literature, or like distortion in the rate distortion theories in mutual information theory. So we can actually use reconstruction error as a lower bound to minimize the reconstruction error, which allows us to maximize the mutual information between x and z. Yes.
I have a high-level question.
Yep.
So are you assuming that you'll have access to the potentially sensitive attributes at both training and test time?
Yes.
So the representation is going to depend on the sensitive attribute, right?
Yes.
So this can be problematic sometimes. For instance, when we are like, when you apply to schools or you apply to jobs and so on, right?
Yep.
And the system is actually not allowed to ask like what your race or gender is. It's strictly optional, and a lot of people actually don't provide that, right? So have you, like, is the overall scheme actually crucially reliant on having, I mean, would it make sense, is there an alternative formulation that would still be sensible if I don't have access at test time, but I still have access at training time so that I can debias my representation?
I think the short answer is yes. We haven't done this in our settings. We did assume that you have the sensitive attributes at test time, but I think it's possible that to create alternative formulations. For example, we can just remove u here from in training, and this allows us to like do testing, because apparently it is possible that x also contains some information about the sensitive attributes, so they are correlated. So you cannot just remove that part simply. I think it is possible. We haven't talked about this scenario, but this is a very interesting potential to think of. So the second problem is that we want to find bounds for the fairness constraints. So we want to minimize the mutual information between the sensitive attribute and the learned representations. So like one easy upper bound that we can apply is that we can simply introduce like an additional variable called here is the x, and the mutual information between the two variables is apparently smaller than the mutual information between one with the other two. And we can use this equation, which here the second term is also like a GAIL divergence that is like greater than 0. So here we can use this term as the upper bound, which is like also present in the like variational autoencoder formulation, and in rate distortion is like called the rate. So I want to sidetrack a little bit and talk about the connection between like mutual information and variational autoencoder. So here we are basically trying to come up with like bounds for this mutual information term, and we already have the upper bound, which is the reconstruction error, and we also have the lower bound, which is the rate. And interestingly, the difference between this upper bound and the lower bound is actually exactly the like conditional VAE objective. So if we remove U entirely, we recover the variational autoencoder objective. So by minimizing this variational autoencoder objective, so we neither maximize mutual information or minimize mutual information. And this view actually aligns with the fact that people have found that like if you have a very powerful generative models, you don't learn very good representations because the variational autoencoder objective doesn't like encourage you to have like representations that are like have high mutual information with the learned with the observations. So this notion has been like we had this notion like in a previous UAI paper, and this is also like related to that topic. However, this upper bound is not very good because the first step we do is we introduce an additional variable, which is x, and we actually need like a better upper bound. So we can actually introduce like a u, the p of u here, which is like a probability distribution over the sensitive attributes that we can predict. This is easier to get because in our applications, the U is usually pretty low dimensional. For example, it could be discrete or it could be like low dimensional continuous. So we can estimate this P of U quite closely to the true distribution just by counting or by like kernel density estimation. So this allows us to get like a similar lower bound, but it's slightly tighter because it operates directly on the mutual information between Z and U. So this is the upper bound. However, we don't actually know this quantity called Q phi of U given Z. So we can actually approximate this with another parameterized model by maximum likelihood. So this goes into the third part, which we could add adversarial training in this case. So we can actually approximate this Q function via a parameterized distribution P by maximum likelihood, which also minimizes the KL divergence. So if we just replace the previous upper bound in Q with P, we have this. And here, this is the maximum likelihood objective, which goes to 0 as we maximize the likelihood. So and this is the case that is tractable. P of U is tractable. The P psi is also tractable. So this gives us something like a lower bound to our upper bound, which is worse than the best case, but still like better because it's a tighter bound. So if we can do this adversarial training to the best, then this also works. So when we actually do the maximum likelihood solution here, our lower bound gap with the upper bound like converges to 0. So this also has a different intuition that where we're basically trying to learn like a classifier and versus a representation learning model. So the classifier tries to predict the sensitive attribute from the representation. And the representation wants to prevent the classifier to predict the sensitive attribute. So this is a type of adversarial training, but this is not exactly like a generative adversarial network case, because the generative adversarial network case attributes predicts only like a binary solution, whether this is in the distribution or not. And in our case, this allows for like any type of U, so as opposed to binary, which is considered in the most previous work. So for now, we have, by applying these upper bounds and lower bounds, we have a tractable objective, which like looks like this. So the first term is the reconstruction error, and the two remaining terms are the adversarial training and the loose rate upper bound. So this we can actually use a dual formulation for this, where we basically choose a Lagrange multipliers, lambda 1 and lambda 2 for the two constraints, and we just choose whatever constraints and optimize for that. And that is actually like used extensively by previous works. So you can just optimize this objective with a fixed lambda. And there are a lot of different previous work that choose like specific lambda and specific type of ways to use this classifier intuition. But interestingly, their method only applies to like two groups of sensitive groups. So your sensitive attributes can only be like binary. And we generalize this case to any type of sensitive attribute via information theory. So this is a generalization to previous method. And given our constrained learning problems, like one very straightforward like way to think of this is like, why don't you also update the Lagrange multiplier as well as your parameters? So it is pretty straightforward to use like dual optimization, as we like maximize also with respect to the lambda, and do minimax with respect to parameters. So here, the intuition is that if the constraint is violated, we just simply increase the weight of the weight of the Lagrange multipliers. If it's not, then we decrease the weight. And this allows us to find the trade-off between fairness and expressiveness implicitly, as opposed to like you have to manually tune the hyperparameters. And this is very useful if you have multiple fairness notions, because in multiple fairness notions, if you have like 10, 20 fairness notions you want to optimize together, you don't want to like tune the individual hyperparameters via grid search or greedy search. So this becomes more complicated as you have multiple fairness notions. And this basically tells us that you want to find a solution that is reasonably fair under multiple notions. And the user only needs to specify epsilon instead of the lambda. And that, I believe, is more intuitive than setting the lambda hyperparameters. So this allows us users to control the level of fairness directly by using this. And if the optimizer cannot find a feasible solution, then it means that the constraint is too tight, or you need a better model, or you need to make the constraints looser. So we have done some experiments comparing the methods. And this is the case where we try to show that our dual optimization method actually can find feasible constraints very closely. So here on the x-axis, we are showing the epsilon values that we set. And on the y-axis is the distribution of the solutions for the corresponding constraint. So for example, in the first plot, we set epsilon 1 to 5, 12, 19, or 26. And we can actually show that the C1 value, which is the value that we compute for the representation, are also like closely correlated with the level that we set. The reason for this is that there's a trade-off between expressiveness and fairness. And it's usually we can get more expressive representations when we sacrifice fairness. So if we set a larger feasible set, the solution would always be like to the limit of the boundary of the feasible set. So we show that in this case, our optimization can actually find feasible solutions like quite empirically quite well. And the second case we want to make is that our method allows us to learn better representations in a shorter amount of compute. So we want to search for the most expressive representation under certain fairness constraints, which is the objective function. And for one method, which is called mutual information fair representations, we have the fixed multipliers. So we basically do hyperparameter search on the fixed multipliers, which is what is used by previous methods. And here we want basically do a grid search over like 25 hyperparameters, and we try to find the most expressive feasible solution. And the other method is basically we also train the Lagrange multipliers on the fly. And this allows us to run this algorithm only for once. And running this for once is also like pretty similar to the compute cost for running one for the fixed hyperparameter settings. So this is the mutual information result that we get for 2 data sets. And it shows that under different levels of constraints, we can actually get more expressive or representation, or like representations with higher mutual information, even compared with using a grid search over the fixed hyperparameters. And in the third case, we want to demonstrate a case where we want to search for the most expressive representations under multiple fairness constraints. So here we consider demographic parity, equalized odds, and equalized opportunity. The last 2 notions can also related to the mutual information methods. So similar derivation of the adversarial training can be done there. So this case, we use a slightly better case where we try to use greedy hyperparameter search. We basically try to first use the hyperparameters that gives you the highest fairness, and then we try to like slightly decrease the highest unfairness, and that we try to slightly increase the lambda hyperparameters, so the representation becomes more and more fair. So once we reach a level of fairness, we can just switch to a next hyperparameter and do the same thing. So this greedy hyperparameter search actually ends up like with 12 runs of the algorithms to find a feasible solution. And for our case, we also just trained the Lagrange multipliers on the fly. this only runs once. And this is the mutual information estimates for the expressiveness and also for the fairness. So it turns out that our method is like better in terms of the mutual information under the fairness constraints. So this demonstrates that we can, if we are allowed to set a control limit for the unfairness, we can actually bypass the process of having to manually tune the Lagrange multipliers. So still, this allows us to learn better representations. So a summary, in this case, we propose a mutual information theoretical view of this fair representation learning, which is closely related to like variational autoencoders and deep generative models, and also with generative adversarial networks in terms of like adversarial training. And because we apply dual optimization, this avoids like tedious hyperparameter tuning and actually learns the trade-off pretty good empirically. And we can actually obtain better representation learned according to our measurements with like less computational resources. Yeah. So these are the like two parts. Yeah.
Because I'm trying to imagine how you plan to use this, and I can see a few different usage modalities, right?
Yep.
So one, I can imagine you just want to have like pre-trained models for generating these representations the same way I would like generate a word embedding or something, right?
Yes.
Download a word embedding.
Yep.
Now, if I were interested in doing this, then I feel like it's very hard for me to commit to what epsilon makes sense, because it really depends on what's the context in which somebody is going to use my representation,
yes,
what kind of predictive task it's going to be employed in, with what kind of hypotheses and so on.
Yes.
On the other hand, if you're thinking that this should really be, okay, so if I have such a setting, then I should just like basically download your algorithm and generate the representation on the fly, then what I don't get is, why do I bother with a fair representation in the first place if I'm in the context of a particular predictive task? Why don't I actually impose fairness on the predictions directly rather than imposing it somewhere upstream where it might, like if you're by making the representation fair, you're trying to say no matter how devious a hypothesis class I come up with, you want to guard against it, right? But
yes.
If I know that I'm just going to use at the end linear classifiers with a bounded norm or something, then maybe I just need like a much smaller preprocessing of the data. And in fact, there are such methods that are like tailored to specific, even not just prediction problem, but hypothesis class and so on, that would provably enforce fairness very well, right? So I guess I'm trying to think of where it makes sense to actually think of fair representation as the right primitive as opposed to fair predictions.
I think the case of like learning fair representations is useful as a primitive when you have like two different parties that are involved in the prediction process. So say one party has the data and the other party has the predictor. So one party gives the data to the another party, which applies their classifier, which uses a hypothesis class that the first party doesn't know of.
What's a practical situation where that arises, where the first party which is releasing the data should worry about fairness? Just help me map it to a concrete task.
Okay, so I think one case that probably is useful is like if you have two companies that share the data. I think recently there's a news where like there's discussions about like Google sharing their data to Apple, and although like it might raise some like privacy concerns, so Apple is trying to use Google's data, and if Apple has the entire data, Google doesn't actually know like whether Apple is going to like do predictions in a fair manner or not.
Yeah, but in that case, probably I actually want to enforce differential privacy or something anyways, because I'm worried about privacy leakage. And if I'm ensuring differential privacy, do I not get something for free about fairness as well?
Oh yeah, I think fairness is actually like closely related to differential privacy.
Right, and there are methods that actually go through the privacy route for providing fairness, right? So
yes. Yes.
So that's why I was again. I guess it's not so obvious to me still when I would want to solve actually an optimization problem like this. for providing a fair representation, because if I'm getting at it from a privacy concern, then I would end up doing something that looks a little bit different.
Yes, that's a very good point. Yeah, so I come from like a deep generative modeling background. So the case that we were thinking about this problem is like to connect this solution with, or the previous solution in this literature with with notions of mutual information and deep generative model notions. So yes, I agree. There's a thing where like whether this notion of like fair representation can be just directly like addressed by like differential privacy or like privacy preserving methods, and I think there's a valid point there. The point that we are trying to make is essentially just we are trying to generalize the previous methods that are like already there, and I think if we are allowed to accept their premises, then our method is essentially trying to like generate these methods. Yeah, but I agree. Yes, so there are probably other methods that are also applicable to these type of scenarios, and they are not necessarily this is not necessarily the only way to do this. And also, I think what's interesting in fairness, like you could have multiple notions of fairness, and this is like probably slightly different from the like differential privacy scenarios. So and I think the potential of using this dual optimization approach is like to show to this community that we can have like much easier methods that allows us to address multiple notions, and which is quite straightforward if you think of this constraint optimization problem route.
So did you, in the context of like downstream prediction problems that you might be interested in, did you compare with directly enforcing fairness on the, say, classifier as opposed to learning fair representation? I'm just very unsure about, I guess, the extent of performance loss that might happen because I'm imposing a stronger constraint.
I see. I think these two approaches are not directly applicable because, directly comparable, because we didn't assume that you actually have the labels in the demographic parity case, right? So if you have the labels, you also want to find a trade-off between fairness and your prediction accuracy. And I think it would be quite straightforward to introduce this objective if you have the labels. So if that's what you are trying to achieve. And when I was doing the testing,
right. So definitely, I mean, you can just think of your X as the XY pair.
Yes.
Right?
Yes.
And that's perfectly fine. But if you are, if you have that structure, then your fairness constraint treats Y as a very special citizen usually, right? Because you're not actually predicting the entire vector anymore. You're just making a potentially point or distributional prediction, but only about that particular Y. So there is still, I agree that a lot of it potentially ports over, but there are interesting differences as well.
I see. Yeah, that's true. So in the equalized odd and the equalized opportunity scenario, you have to choose. At least in this case, you have to choose for a particular Y, and we could potentially deal with multiple types of Y. That's like one way out. I guess the other way out, if you know what Y you are just dealing with, then you should just use prediction directly. And I think the representation case only it's mostly suited for like unsupervised cases where you don't necessarily know what are the downstream costs your users are going to use. So I assume that in the case that Google knows some task and then like Apple wants to do some different task, and it doesn't tell Google what task it is going to use. So I guess the best course of action for Google is to just use whatever Y they have to protect the representations, I guess. Yep.
So I had two questions, one for the first part and one for the second part.
Yep.
For the imitation learning bit, this view of occupancy measure matching, I'm curious if that's making a bunch of strong additional assumptions that maybe existing imitation learning methods are not making. So, does it crucially require that the experts have a stationary policy? Does it crucially require that the experts' policies are close to optimal? basically, I mean, I can imagine like existing methods that are doing more in like matching action sequences are maybe more robust. It's fine if the experts' policies are suboptimal because you can just use that as warm starting and still get something reasonable out. Whereas maybe this occupancy measure matching is more brittle to those kinds of assumptions.
I think that the case is like similar. That is like one of the reasons why like using regularization is important. So so here like one of the assumptions is like your expert like acts optimally or close to optimal in the reward, and another like useful case for like inverse reinforcement learning that we haven't touched like very deeply with is like the can you utilize the reward function that you have learned? So the short answer for GAIL is no. The value generated by the discriminator in convergence doesn't give you a reward because when the GAN training converges to optimal, then everything is like 0.5. However, by modifying this GAIL formulation slightly, you could actually retrieve the so-called true reward under some assumptions. So one of the assumptions is very important is the maximum entropy reinforcement learning. So you would assume there is like a fixed trade-off between the entropy, actually it's like gamma-induced entropy, and the reward function, and that is also maybe a slightly strong assumption because I think in practice everyone would say that there's not necessarily like a fixed trade-off between the entropy and the reward. So I would say that this the use case is for IRL is also like related to how you would treat what reward you learn, and I think it's very important in the multi-agent setting because if we happen to like recover the reward, then you can use this as a way to guide like gain insight about the demonstrations. For example, in the self-driving case, it's very hard to analyze for like each agent what's their reward is necessarily. But if we can retrieve this, then we can use this to analyze the behavior of like particular agents or the society as a whole.
The second question was for the fair representation stuff.
Yep.
So I'm just trying to build intuition about this. So is this, say I'm looking at the mutual information the way you defined it.
Yeah.
Is this a binary sort of thing, or is this like if I've managed to get lower mutual information, does that mean I have done a proportionally better job in protecting a sensitive attribute, or is it actually a 0-1 kind of thing? Like I better get the mutual information below 0.001 because anything beyond that, I'm actually not fair. I'm like I've made progress in like maybe lowering the mutual information, but I haven't really protected that sensitive attribute.
I see. So this is the reason why we want to set a positive limit on this is because of the impossibility solutions, right? So you cannot be fair across everything. Right. So you have to make some trade-offs, and there are different ways to specify the trade-offs. And the way that we introduce to specify the trade-off is that you have a limit of unfairness for each of the attributes. And so essentially this problem means like if my information is lower than some point, then I don't care then I don't care about this.
How does this notion like map to the real world? Like is there any consumer in the real world who's happy with this notion of like I'm allowed to violate any one of these fairness constraints up to a limit?
I see. I think you could derive something like for like a particular label, like how using this representation could violate fairness. I currently couldn't think of how exactly you could do this, but I think you could connect mutual information with like how good you can predict something with one of the variables. So this, I think the mutual information allows you to connect this with the predictability of the sensitive attribute, and also this allows you to sort of measure how unfair you could be like at its maximum. Yeah.
I have a high-level question for your first part of work. Yeah. I might miss it when you talk about it. I didn't get like how could you generalize beyond the expert demonstrations? Like, what's the main advantage of doing this compared to the traditional approach, like IRL approaches that directly learns the reward function or transient dynamics from the expert's demonstrations?
So one of the advantages of this is like it allows you to incorporate your prior knowledge to the reward via the regularizer. I'm not sure if that's what you're asking about.
Yeah, but I feel like also the reward function or transient dynamics, if you try to learn that, is also sort of incorporating this kind of prior knowledge. I'm saying like what kind of prior knowledge you can incorporate by doing this, or it's kind of similar to this. Also like transition dynamics, reward function, things like that.
I don't think we have talked about regularization on learning the transition dynamics or the model-based setting.
Okay.
I think we are mainly talking about the model. Like you can essentially solve this problem via model-based reinforcement learning, but here we mostly think about the model-free case where, given a reward, you can recover some policy, and because in the assumptions of maximum entropy RL, there is like a one-on-one mapping between like reward and policy. So this is like the reason why you could recover the reward like from the policies. Yeah, and then like because maybe there is some like prior knowledge that we want to incorporate, we can use this regularizer on top of the reward to get the reward that we actually desire, I think. And previously, I think the methods for like inverse reinforcement learning usually talks about cases like where your reward is like maybe linear in the features or some like simpler settings. So I think the GAIL case is mostly discussed about the potential of using a regularizer to potentially like shape the reward in the way that you want, as opposed to like proposing any kind of reward. Yeah, I guess that's it. And thanks for attending and staying for the talk. And if you have any other questions, just send me an email, let me know, or I'm happy to chat like these 2 days, like Monday and Tuesday. All right, thanks.